I want to graph this function. Now, this is a square root shape, I can tell, but it's got several transformations applied to it. I need to figure out what those are. So I'm going to spend a while talking about transformations in a general sense, and then I'm going to attack this specific example. Now, one thing I've talked about is that a way that you could get all graphs done accurately is to use one specific ordering, and it's not the only valid strategy for graphing, but this ordering will work. You can start by doing the left-right shift, and in this case you can see that there's a +3 corresponding to the left shift. The second thing would be to reflect about the y-axis. It's like a horizontal flip, I suppose, and then a horizontal stretch or compression, depending on how big that number is. Now, these two steps, reflecting about the y-axis and doing a horizontal stretch or compression, they are interchangeable. That's why I have them on the same line. The next step is to reflect about the x-axis. That's just like flipping upside down, or doing a vertical stretch or compression. And again, those steps are interchangeable. And finally, you would do the up-down shift. So for a super generic square root graph where maybe there's a plus or a minus here, maybe there's a plus or a minus here, b is a real number, maybe it's 1 or 2 or 3, or maybe it's 1/2, c and d can be any constants. So what I'm trying to say is that c corresponds to step 1. It'll tell you whether to shift left or right. The B tells you what the horizontal stretch or compression should be, and if that B is negative, then you know to also do a flip. The A tells you about the vertical stretch or compression, and if there's a minus in front of the A, you know to reflect across the x-axis. And finally, that plus or minus D tells you whether to shift up or down. So now I am going to talk about this specific function. That +3 will come first. We will shift our square root shape left 3 units. Then I see the -2 out in front. The 2 means twice as tall, stretching out vertically, and the negative means reflecting across the x-axis, flipping upside down. And finally, that -1 means shifting down 1 unit. So some very rough sketches can show that taking our little square root shape and shifting it to the left makes that little vertex B at -3. You can make that shape taller, you can flip it upside down, and then you can shift it down. So roughly that's the shape that we're looking for this graph. Now, here is our function again, and here is a nice set of axes. This is an original square root shape. It goes through the points 0, 0, 1, 1, 4, 2, and 9, 3. And the first step is to shift to the left 3. Now, can you see that 0, 0 here needs to shift to the left? So I've plotted -3, 0. 1, 1 has to shift to the left, and it turns into -2, 1. 4, 2 shifts into 1, 2. And so you can connect those and make a square root shape, and that's going to be radical x + 3. So we've done the first transformation. Second thing we have to do is stretch it out so it's twice as tall. That means all the y coordinates of the blue curve are going to be twice as high. -3, 0 doesn't change. -2, 1 turns into -2, 2. 1, 2 turns into 1, 4. And so I can connect those dots, and I'm going to get 2 times radical x + 3. My next transformation is to reflect across the x-axis. That means taking that green shape and reflecting it across this line right here. Now, -3, 0 isn't going to change, because 0 minus 0 is equal to 0, right? But check out -2, 2 here. That 2 is going to turn into -2, so that's what I want to plot. This point, 1, 5, turns into 1, -4. 1, 4 turns into 1, -4. You connect those dots, and you get y equals -2 times radical x + 3. Now there's one last transformation, and that's shifting down 1 unit. So that negative 3, 0 finally is going to move, and it's going to turn into negative 3, negative 1. That negative 2, comma, negative 2 will turn into negative 2, comma, negative 3. All of the dots in the red curve are going to shift down 1. And we can connect those, and we get the final equation of our final curve. From this graph, I can tell what the domain and range are going to be. I can see that my curve goes from negative 3 all the way up to infinity. So my domain is negative 3 to infinity with a bracket on that negative 3 to show that the negative 3 is included. I can also read the range. I can see that the graph does hit a height of negative 1 and it goes all the way down. And so my range is negative infinity to negative 1 with a bracket on the negative 1. Now the domain I could have gotten in other ways, but the range, the only thing I know how to do is read it from the graph. So it was really important to graph before I could tell what the range was. You might be wondering, and it's really fair, is there a better, faster way to do this? And in this case, there is one other strategy that we could use. Now, the first thing is to figure out the domain. I said we don't need the graph to figure out the domain in this case. What we do is we set x plus 3 greater than or equal to 0. That's because we can't take the square root of a negative. So we take the stuff under that radical and set it greater than or equal to 0 to solve. That's another way to get that negative 3 to infinity interval with a bracket on it. Once you figure out the domain, we're just going to make a table of values. Here's the secret. I need x values that make x plus 3 a perfect square. I want that to be equal to 0, 1, 4, 9. I can reverse engineer and pick x's that make easy y's come out, which is really cool. So I'm going to pick negative 3, negative 2, 1, and 6. After I'm done making my table, I'm going to plot those points and just connect them, make the shape. So here's my table of values. What you can see is after I plug in this x and I add 3 to it, I get a perfect square. So negative 2 times radical 0 minus 1 is just negative 1. Plugging in negative 2, I get a radical 1, which is great. I know exactly what that is without a calculator. My y value is negative 3. You plug in 1 into this function, you get negative 5 as a y value. You plug in 6. 6 plus 3 is 9. That's a perfect square. So you get negative 2 times radical 9 minus 1, and that's equal to negative 7. Could you have plugged in other x's like negative 1 and 0 and 2? Absolutely. But your y values wouldn't have been integers, and so in a sense that's a bit annoying. So I like these x's instead. Here are some axes. There I've chosen to plot negative 3, negative 1, negative 2, negative 3, 1 comma negative 5, and I'm going to connect those dots and make my graph. So in this case, I feel that that process was a little bit shorter in creating our graph.